Okay, so good morning to everyone. So as Nicola said, I'm gonna now explain how we can compute the Hubbard parameters from first principles using linear response theory. Yeah, this is a brief recap of the previous lecture by Professor Coccocioni. So we just saw this expression for DFT+U, the energy functional, where total energy is the DFT total energy plus the Hubbard U corrective term, where U is the unknown Hubbard parameter and N are the so-called occupation matrices defined as projections of Conchem functions on the localized orbitals phi. And F are, let's say, Fermi-Dirac occupations or any other type of occupations. And more generalized formulation or extended formulation is DFT+U plus V, where we have not only the on-site localization term, but also the inter-site, let's say, hybridization term. Just schematically represent what these terms do. So the plus U term wants to localize electrons more. I show it in blue. So we apply the U correction on the D or F electrons of atoms in the center of the octahedra. And the second term V, which is the inter-site interaction in magenta, it describes interaction between neighboring atoms. Let's say the transition metal in the center of the octahedra and oxygens in the corners of the octahedra. So let's say in DFT we have delocalization error due to self-interaction. So the D electron is over delocalized, too much spread out. When we apply the plus U correction to this D electron, it localizes more, so we can represent it as sharper Gaussian. And if we put plus V, we keep the localization thanks to plus U, but at the same time we restore the hybridization with ligands, in this case, oxygens, p electrons. As you saw already during day one, but in the talk of Professor Marzari, there are two strongly interconnected key aspects in the Hubbard functionals. On the one hand, we have Hubbard parameters U and V that are not known, and we have to determine them somehow, and this will be the topic of this talk. And on the other hand, we have Hubbard projectors. These are those functions phi onto which we project the Conchem functions. These Hubbard projectors are also not uniquely defined. We can have different types of Hubbard projectors. And I will also discuss about this more in the remainder of my talk. So let's first talk about Hubbard parameters, how to determine them. So the values of Hubbard parameters are not known a priori. The theory doesn't tell us what are the values of Hubbard parameters. And there are two famous strategies how to determine them. The first strategy, historically, it was used the first, and it's one of the most used in the community, is the semi-empirical determination of Hubbard parameters. So what we do, we just tune the Hubbard U parameter such that we reproduce some properties of interest, such as band gaps, magnetic moments, lattice parameters, oxidation enthalpies, and you name it. However, in order to determine Hubbard U in this way, we need to have some reference experimental data. However, as we all know, not always we have experimental data, and sometimes it's not very accurate. So what do we do if we want to study some novel materials for which we don't have any experiments? In this case, we can't really determine the Hubbard U parameter. Of course, we can use Hubbard U parameter from other similar materials, but as I will show in the next slide, Hubbard U is not universal, so it's not really transferable. So that's why we need to be careful, and this strategy is not always easy to use. And the second strategy is really to determine the Hubbard parameters from first principles. And there are several methods to do that. So I would like to mention about the constrained density functional theory, CDFT. Another popular method is constrained random phase approximation, CRPA. Then there are other methods based on Hartree-Fock approach, such as maybe you've heard about ACB and zero functional. And another one is the linear response theory, which will be the topic of this presentation. So this is, in this slide, I wanted to summarize very important take-home messages. So I hope after this talk, you will really remember this slide by heart, because this is really fundamental if you want to use DFT plus Hubbard in your research. So computed Hubbard parameters depend on many aspects. First is the type of Hubbard projector functions. These are those functions in the yellow rectangle phi. So as I said, there are many options. For example, atomic orbitals, which are obtained from pseudopotentials. So the code reads pseudopotentials and reads the information about atomic orbitals. Another option, orthoatomic or loading orthogonalized atomic orbitals. This is different from the atomic orbitals in the sense that we just take atomic orbitals of all atoms in the system and we orthogonalize them using the loading method. I will talk a little bit more about this later in my talk. Another option is to use maximally localized Vanier functions. We heard about them yesterday a lot. So why not using these functions? And then there are other options. So it's really, in different codes, you have different options. If you use quantum espresso, you have atomic, orthoatomic, and we are working on maximally localized Vanier functions. If you use VASP, you have yet another type of projectors, which is based on the projector augmented wave method. If you use VN2K, it's yet another option. In Abinit, you have truncated atomic orbitals, and siesta is something else. So yeah, so you have to be careful. If you use the Hubbard-U parameter of, let's say, 5 electron volt, in different codes, you will obtain different results because the Hubbard projectors are different. So that's the common mistake, actually. So one has to be very careful when taking the Hubbard-U parameter from other papers, from different codes, and try to use it with different code for your research. Also, Hubbard parameters depend on pseudopotentials and the oxidation state. I invite you to check this reference at the bottom by Kulik and Marzari. So in the appendix of this paper, they show that you can generate pseudopotentials, let's say for iron, in different oxidation states. And then if you use these different pseudopotentials with linear response theory, you will obtain different values of Hubbard-U parameters. But then if you use these different Hubbard-U parameters with respective pseudopotentials consistently, you will actually obtain results which are very similar. Also, Hubbard-U parameter that you compute with linear response theory depends on the exchange correlation functional. If you use LDA or some version of GGA like PBE, PB-Sol, the value of Hubbard-U will not be exactly the same. It will change. If you want to use scan, it will be yet another value. And the cell consistency, I will discuss about this later in my talk, but essentially you can determine a Hubbard-U parameter in one-shot fashion or self-consistently. So I will explain it later. So let's keep it for later. So you see there is already many factors that influence the value of the Hubbard-U parameter. So it's not really universal. It's really system dependent. It depends on which methods you use, which Hubbard projectors, which pseudopotentials, which functional, etc. Okay, now let me explain how we can compute the Hubbard-U parameter. So here I show at the top of this slide the expression of the energy functional. I simplified it a little bit. So I consider just one transition metal atom. I removed the summation over atoms and spin. So this is just for simplicity. So N in bold is the matrix. And if we take the trace of this matrix, the sum of the diagonal elements, it will give us the scalar object N. And we also saw this similar picture earlier in the earlier talks. So the main idea is that Hubbard corrections remove the spurious curvature of the energy. So the exact behavior is piecewise linear. This is the total energy as a function of the number of electrons in the Hubbard manifold. The approximate DFT gives quadratic-like behavior. And what we want to get rid of these curvatures. So I indicate them with black arrows. So we want to remove the curvature. And how do we compute the curvature? It's simply the second derivative of the total energy with respect to the number of electrons in the Hubbard manifold. If the second derivative equals to 0, the curvature is 0, no curvature, it's a straight line. So from this condition, we can actually obtain the expression for the Hubbard-U parameter. how you take the expression for energy at the top of this slide, you compute the second derivative with respect to n, and you will find that u is equal to the second derivative of the DFT total energy. It's very simple. But then how to use it in practice? It's a bit more tricky. So the DFT energy functional, it's a functional of the spin charge density. So E DFT depends on the spin charge density rho sigma. But what we want to compute is the derivative of this object with respect to the occupations. So the DFT total energy is not a function of occupation. So we cannot straightforwardly compute this derivative. So that's why we need to do some math. And this is explained in this paper at the bottom. So what we do, we construct a new object. Energy is a function of lambda parameters. And what we do here, we use the Legendre transformation, which is simply the sum of the DFT total energy plus this second term, where we have lambda I. These are the coefficients, and ni are the occupations. Then what we do, we minimize this expression with respect to the spin charge density. By doing so, we obtain this object E of lambda I, and then we can construct yet another object, E bar, which is the energy function, which depends on the occupations n of I. So this is obtained by subtracting from our energy expression E of lambda I, the term that we added before. So we subtract it now. And now we can compute the first and the second derivative of the E bar object. So the first derivative with respect to n of I is simply minus lambda I. And the second derivative is the derivative of lambda I with respect to n, with we keep the minus sign, of course. And we call this object chi to the power minus 1. So chi is the so-called response matrix. And finally, we can define the Hubbard U parameter as we said, it's the second derivative of the total energy. So that's why we write minus chi to the power minus 1. But there is one more trick here. We subtract one term, which is minus chi naught minus 1. So this is the bare response matrix. And this object is not related to electron-electron interaction. So we need to remove it. And if we massage a little bit this equation, we obtain chi naught to the power minus 1 minus chi to the power minus 1. So I repeat that chi naught is the bare response and chi is the self-consistent response. So we can rewrite this equation in a different way as chi equals chi naught plus chi naught u chi. This is the so-called Dyson equation, where chi naught is the non-interacting response and chi is the interacting response. So that's another way how to see why you need this chi naught term. And that's it. That is our final expression for the Hubbard U parameter. Okay, now how to use it in practice. So this is summarized in this slide on the figure on this part on the left. So we need to construct, we need to solve the modified quantum equations written at the top of this slide, where H is our Hamiltonian. Then we are adding the extra term, which is lambda and the perturbing potential. The perturbing potential is simply the projection on the localized orbitals phi. And lambda is the strength of this perturbation. So in practice, we use some small positive value and some negative value. And this is equal to the eigenvalues multiplied by the wave functions. In practice, we need to use supercells, as shown on the right, and we need to perturb transition metal atoms one at a time. So I highlighted in yellow color the perturbed atom. So why do we need to use supercells is because we are using periodic boundary conditions. So if we use a primitive cell, and we perturb one atom, we have periodic replicas. So the perturbed atom will interact with its periodic image, and this will lead to unphysical interactions and unphysical effects. So that's why we need to construct a large enough supercell in order to reduce as much as possible the interaction of the perturbed atom with its periodic image. And then by doing so, we solve the modified conjugate equations in a supercell for two values of lambda. And using finite differences method, we can compute the derivative, the change of the occupations with respect to the perturbation, delta n with respect to delta lambda, and this gives us the self-consistent response matrix chi ij. Then we simply invert this matrix, we obtain chi to the power -1. We also can determine chi naught -1 after the first iteration of the perturbed run. So when there is not yet a Hartree exchange correlation readjustment to the perturbation. And then we take the difference of these two objects and we obtain the Hubbard U parameter. So the Hubbard U parameter is the diagonal term of this difference of the response matrices, while the V is simply the off-diagonal term of the difference of the inverse response matrices. However, this approach, it's very successful. If you can see the number of citations of this paper, I think it's more than 2,000. It's really widespread approach. It's pretty simple idea, and it works in many cases. However, there are a number of challenges here. First is that this method is computationally expensive because we need to use supercells. There are possibly convergence issues when we use large supercells, as we know. And it's a bit cumbersome to use in practice because you need to do a number of post-processing steps. Of course, you can write Python scripts to do that automatically, but if you don't have those scripts, it's a bit not user-friendly post-processing part. And in recent years, we actually addressed this issue, all these challenges, by recasting the linear response theory of supercells using a more efficient approach, which is based on density functional perturbation theory. And I'm going to introduce you to that. So let me first talk about the link between the primitive unit cells and supercells. Let's take a primitive cell, for simplicity cubic, two-dimensional, and AI is the length or the lattice parameter of this primitive unit cell. We can construct a 2x2, let's say, supercell in red. And now we are actually doubled the length of the lattice parameter. We use the capital letter A to indicate the lattice parameter of the supercell. And it's equal to the lattice parameter of the primitive cell times the number of units in each direction. Okay, now what about the Brillouin zones of these two lattices? For the primitive cell, we have a larger Brillouin zone, and for the supercell, we have a smaller Brillouin zone. This is because if we have small cell in real space, we have large Brillouin zone in reciprocal space, and vice versa. So if we label small b the length of the Brillouin zone side, and with the capital B, we indicate the length of the Brillouin zone that corresponds to the supercell. And if in real space, the A is Li times AI, so in the reciprocal space, it's vice versa. It's actually L times smaller than the size of the Brillouin zone of the primitive cell. Now, for these two Brillouin zones, we can define a generic reciprocal lattice vectors. So in the case of the primitive unit cell, we can define a generic reciprocal lattice vector small g, which is defined in terms of B1, B2, B3, and where K prime, L prime, M prime are some integer numbers. And in the case of the Brillouin zone of the supercell, we also can define a generic reciprocal lattice vector, capital G, which is defined in terms of capital B1, capital B2, and capital B3. And K, L, M are also integer numbers. Okay, that was pretty basic, nothing extraordinary here. And now this is really the key slides. So this is the expression of the generic lattice vector of the Brillouin zone corresponding to the supercell. And since we know that capital B is small b divided by L, we put it in the definition. It's what we obtain, this modified expression. And then here we tell that we can actually write these indices K, L, and M in this form, where we introduce K prime, L prime, M prime, and K bar, L bar, and M bar. So K bar, L bar, and M bar are remainders, and these are quotients. And by using this definition, it can be shown that actually the reciprocal lattice vector capital G can be written as a sum of the reciprocal lattice vector corresponding to the Brillouin zone of the primitive cell plus some Q vector Q. And these objects, small g and small q, are defined on the right using the definitions above. So this is really the most important result of these two slides, that we can write the generic lattice vector of the supercell as the sum of the generic lattice vector of the primitive cell plus some Q vector. Sorry, maybe it was a bit too technical, but I think we had to go through this. And now this is a final slide about this aspect. Now we take the Fourier expansion of the perturbing localized potential in supercell V of R and write it as the sum over reciprocal lattice vectors capital G, the phase factor exponential to the IGR, and the Fourier coefficients V of G. So this is object written for the supercell. And then we can rewrite it a little bit in more detail, because we know that G vectors, they depend on indices KLM, so we write it a bit more accurately. And here we use the result of previous slide, that we can represent this capital G vector as the sum of the small g vector of the Brillouin zone of the primitive cell plus some Q vector. By doing so, we use this definition in the expression above, and we can, after some steps, which are really simple ones, we essentially obtain the result that the potential V of R of this in the supercell can be written as a sum over Q points or Q vectors with the phase factors exponential to the IQR and some new objects V bar Q of R, and these objects are defined above. These are lattice periodic objects. So what we did here is that we wrote the potential of the supercell as the sum of the so-called monochromatic components and the potential defined for the primitive cell. And this is really the key result that allows us to reformulate the linear response theory to compute Hubbard parameters in more efficient way using primitive cells instead of supercells and using density functional perturbation theory. So that brings us to this slide where we make this transition from the old approach based on supercells to the new approach based on primitive cells. So as we saw before, on the left slide, we see the modified quantum equations that we had to solve by inserting the perturbation inside of our equation, lambda V perturbation. Now what we can do, we can expand this equation. Each of these objects we expand in Taylor series and truncate it at first order. And what we obtain is the first order linearized equation, which is written here. So this is simply the perturbation theory and Taylor expansion, nothing special. So in this equation on the right, so instead of equation on the left in yellow, we solve equation on the right in yellow. So dv psi over d lambda is the response of the wave function. dv Hart exchange correlation over d lambda is the response of the Hart exchange correlation potential. The epsilon over d lambda is the response of the eigenvalues. And V perturbation is the original perturbing potential. So now we need to solve this equation on the right instead of the equation on the left. Then we use the fact that we can represent the potential of the supercell as the sum of the monochromatic components in a primitive cell. So combining these two ideas allows us really to simplify the problem greatly. So now we just use primitive cell and many monochromatic perturbations instead of one isolated perturbation in a supercell. And instead of using finite differences on the left, in this pink rectangle where we had to use finite differences, now we actually don't use finite differences. It's really the analytical expression for the change of the occupations, dn over d lambda. It's written as the sum over q components, some phase factor, and delta q of n, which are the response objects computed in the primitive cells at different q perturbations. And that's it, essentially. That's the main idea of this. So as I told you, this is called density functional perturbation theory. We use primitive cells plus monochromatic perturbations, the Q point grid. So what are the advantages of this new approach? Is that it's computationally much less expensive because we simply use primitive cells and not computationally expensive supercells. It's easier to converge the calculations. As we know, with primitives, it's always easier to deal with primitive cells rather than supercells. And this approach is user-friendly and autonomous. It's implemented in the HP code in Quantum Express, and we will use it during the hands-on. So this idea of going from supercells to primitive cells with monochromatic perturbations is not new. It was used 2 decades ago, or even 3 decades ago, to be more precise, to compute phonons. This is the famous phonon package of Quantum Express. And also tomorrow you will learn that exactly the same idea can be used for Koopman functionals to determine the screening coefficients. So this idea is very general and it has applications in for many problems. And this is one of those applications. Yeah, this is just a summary of all this theory. If something was not clear, or you want to go in more details, take your time. So I really invite you to check these 3 papers. The first 2 are methodological about the theory. And the last one at the bottom is about the HP code that implements these ideas and is publicly available through the Quantum Express package. Okay, we have 15 minutes more, so let me continue. So how does it work in practice? Is the new method really faster than the old one? And the answer is yes. Just if you take and consider scaling for nickel oxide. So on the y-axis, we have the CPU time in hours. And on the x-axis, we have the size of the Q-point grid, which is equivalently corresponds to the size of the supercell. So if you use supercell 2 by 2 by 2, this means you need to use primitive cell with the Q-point grid 2 by 2 by 2. If instead you use supercell 4 by 4 by 4, you need to use primitive cell with the Q grid 4 by 4 by 4. So it's really one-to-one correspondence. And we can see that the speed up is really huge, factor of 52 for the size of the supercell 4 by 4 by 4. So it's really a big factor. It allows us to save a lot of computational resources. And on top of that, we can use symmetry. This is very powerful because this allows us to reduce number of Q points. While in the supercell approach, you can't reduce number of atoms. You have supercell 4 by 4 by 4, and you can't reduce number of atoms. You need to run this expensive calculation. While with Q points, with symmetries, it's like with K points. You know, when you sample the brilliant zone, you can use the reducible wedge of the brilliant zone for K points. Same for the Q points. So we really can reduce number of calculations. And if we compare the numerical values of Hubbard parameters contained using linear response supercell approach and DFPT approach, by taking care of the correspondence of the K-point sampling, we will see that they really agree very well and within the numerical noise. We can push those numbers to be even closer if we push a little bit more the convergence parameters. And now that's the slide about the convergence of the Hubbard U. As any other property, we need to converge the Hubbard-U parameter with respect to cutoff, with respect to the K points, with respect to the Q points, etc. So here I would like to show you how the Hubbard-U of nickel 3D states in nickel oxide converges with respect to the Q point mesh and K point mesh. So you see, we really need to increase the K mesh and Q mesh until the Hubbard-U parameter doesn't change, or we converge it to certain precision. Let's say in this case, we can tell that the converged value of the Hubbard-U is 8.18 electron volt, and this can be obtained using the K mesh 8 by 8 by 8. So this corresponds to the green curve, and the Q mesh 5 by 5 by 5. So this means we take this dot here. So that's our converged value. Okay, that was all about the Hubbard parameters. Now let's talk about the Hubbard projectors, which are also very important aspect, and which is always overlooked or forgotten in the papers. People don't really pay much attention to which type of Hubbard projectors do they use. As I told you earlier in this talk, we can have different types of Hubbard projectors, like non-orthogonalized atomic orbitals, which can be simply obtained from pseudopotentials. Second version is the orthogonalized atomic orbitals. Here we compute the overlap matrix O by simply computing the scalar product between atomic orbitals. Then we take the inverse of this overlap matrix to the power 1/2 and multiply it by the original atomic orbitals. And this gives us a new orbital phi tilde. Another option is maximally localized wave functions. This is a very interesting direction, and we are exploring this type of projectors. And as I told you, if you use different types of Hubbard projectors with the HP code that is based on DFPT, you will obtain different Hubbard parameters. In particular, in the case of nickel oxide, if you use non-orthogonalized atomic orbitals, you obtain U of 6.76 and V of 1.25. But if you use instead orthogonalized atomic orbitals, you obtain U equals 7.43 and V 0.37. So you can see that these numbers are not at all the same, which really confirms what I was saying, that the values of Hubbard parameters are very sensitive to the type of Hubbard projectors. So the take-home message is that it is crucial to keep consistency between Hubbard projectors and Hubbard parameters. So if you computed Hubbard parameters using orthogonalized atomic orbitals, you need to use those values with the same type of projectors for production calculations. And the question is, which type of Hubbard projectors should I use? From our experience, the orthogonalized atomic orbitals is more accurate than non-orthogonalized ones. And also they are more accurate because in the overlap regions, we don't apply the Hubbard-U correction twice. So if you imagine two atoms and the orbitals that overlap, if you use non-orthogonalized orbitals, it means that you apply Hubbard-U correction to one atom to the second, but in the overlap region, you have the correction applied twice, which we don't want. If instead you use orthogonalized atomic orbitals, you don't have this problem anymore. And I will show you at the end of my talk that indeed, orthogonalized atomic orbitals give more accurate results. Maximal localized value functions is also a great choice, and I think it should be as good as orthogonalized atomic orbitals, or maybe even better in some cases, I don't know, but we are exploring this direction. Okay, this is again to try to convince you that it is important to stay consistent when you compute Hubbard parameters with certain type of Hubbard projectors. If we take the cathode material that was discussed in the previous talk by Matteo, and we consider two cases. In green, I show you full consistent case where the computed Hubbard parameters are consistent with the Hubbard projectors that were used also for the structural optimization. And in red, I show you not consistent case where Hubbard-U parameters were obtained with orthogonalized atomic orbitals, but the structural optimization was done, these values with non-orthogonalized atomic orbitals. So there was some mismatch between the values of Hubbard parameters and type of projectors. If we look at the lattice parameters for this material, when there is no lithium, we see that green bars are in closer agreement with experiments than the red bars. And same for the voltage, we see that the green bars are closer to experiment than the red bars. So that's really showing you that it is important to be consistent. And this is what I was mentioning also earlier in my talk, when I was talking about one-shot calculation of Hubbard parameters and self-consistent one. So what we use is the so-called self-consistency workflow. It's discussed in the paper below, and it also was actually introduced earlier than this work, maybe more than 10 years ago by Matteo and Renata Vinskovic and other co-workers. You will hear about Renata's talk later today. But the idea is the following. You choose the initial structure, let's say experimental one or from database, COD, ICSD, you name it. And you can in principle have initial guess of Hubbard parameters. If you don't know anything, just use 0. But if you have some initial intuition to which values you should have, you put those in initial intuition for Hubbard parameters. Then you perform DFT+U+V self-consistency ground state. If you don't have U and V, it's 0, so it's simply DFT ground state calculation, as we did yesterday. Second, you use DFPT, the HP code, to compute the Hubbard parameters. So this gives you U out, V out. And then you can perform structural optimization at the DFT+U+V level using the U and V determined in the previous step. So in principle, here you can stop and you say, this is my one-shot calculation of Hubbard parameters. But actually, there is a question. I mean, you computed Hubbard UAV parameters starting from the DFT ground state and experimental geometry, but those parameters are not yet consistent with the underlying structure. So what I mean is that if we go back and we say U initial equal U input equal U output and V input equal V output, so now we perform a new ground state calculation with the new Hubbard parameters, and then we recompute again the Hubbard parameters. They will have different value. This is so because we perform structural optimization using U and V. So our ground state has changed, our geometry has changed, and that's why also the U and V will be different. So now with updated U and V, we do a new optimization. So now again, the structure changes a little bit. And we go one more time back, we recompute ground state. Essentially, we do this double loop. One loop is the structural optimization, and second loop is the recalculation of Hubbard parameters. So we do this loop until the U input and U output, they start matching. So the difference is smaller than some delta threshold. And same for the geometry. Geometry starts converging to some final geometry. So when we cycle this until Hubbard parameters converge and structure converge, so we exit this double loop and we say we reach the full self-consistency between electronic degrees of freedom and structural degrees of freedom. So now our self-consistent Hubbard parameters are fully consistent with the underlying geometry. And we will show you that this is the procedure that we use in practice. Not one-shot one, but really the self-consistent one. So in this procedure, we need to perform structural optimization at the DFT+U+V level. And here this brings us to the discussion about Hubbard forces and stresses, or they are known as Pulay forces and stresses. There was a question on Slack, but I can profit and discuss 1 minute about it here. So in the DFT+U formulation, or DFT+U+V, when we compute forces, we have extra terms due to the +U term and +V term. This force is defined as the derivative of the Hubbard U correction with respect to the atomic displacement tau. We can represent this derivative as the derivative of n with respect to occupations and derivative of occupation with respect to tau. So the first term, it's easy to compute. It gives us U Kronecker symbol minus 2n, and the second term we keep. So we highlight it in green. If when we use the definition of the occupation matrix n, we can write what is the expression for its derivative, dn over d tau. It's this quite long expression, and the main quantity that we need to compute is this expression in yellow, the derivative of the scalar product between the lattice periodic part of the Konchevy function u with the block sums of the localized functions phi of m. That's why it has the index k. So this object is not so easy to compute. Actually, it can be shown that it's simply the scalar product of u and the derivative of the localized function with respect to tau. And that object finally can be expressed as the sum of the two terms. The first one is the derivative of the overlap matrix O to the power minus 1/2. And the second term is trivial. It's just the derivative of the block sum of the localized orbitals. So the main issue here is how to compute this object, the derivative of the overlap matrix to the power minus 1/2 respect to displacement. It's not a scalar function, so it's not so easy. It's a matrix to the power minus 1/2. And we solved this problem a couple of years ago. I don't want to go into details because it's pretty involved. I want to just tell you that we found exact solution to this problem. So this object can be computed by solving Lyapunov or Sylvester equation. There is exact analytical expression. It's implemented in quantum espresso. And we just tested that it really gives the exact solution. We compared the analytical formula with the finite differences approach in lithium cobalt dioxide, and we saw that the force is computed with finite differences, and using this analytical expression they match to high level of precision, which confirms the correctness of the derivation and the implementation. The same exercise was done for stresses. And this is how it looks like, the convergence of Hubbard parameters with respect to the when we use the self-consistency workflow. Just let me take one of those. Let's say we take left-hand side figure and the top panel, and let's look at this blue curve. This is the value of the Hubbard U parameter for manganese 3D states in manganese phosphorus 4 as a function of iterations, iteration 1, 2, 3, 4. So each iteration, it means we performed structural optimization and recomputed Hubbard U parameter. So if we do the first iteration, it means we took experimental geometry, optimized it with at the DFT level, with PB solve functional, and we computed Hubbard U, and we obtained 5.6 or something. In the second iteration, we performed structural optimization at the DFT+U level, and U was 5.6. So our geometry has changed, and we recomputed Hubbard U, and now we obtain a new value, which is 6.1. So you see, it doesn't stay the same. It went from 5.6 to 6.1. In the third iteration, we re-optimized structure again using U of 6.1. So the geometry has changed a little bit less than before, from step 1 to 2. That's why Hubbard U also changed less. It went from 6.1 to 6.2. And we do one more iteration, we see the geometry doesn't change almost, and also the Hubbard U doesn't change almost, it stays almost the same. So that's why we say we've reached the self-consistent U value of 6.19. And this is different from the one-shot value, which is 5.6. So we use 6.19 for production calculations. And in the remaining maybe 1 or 2 minutes, I just want to show you how it works. You just saw a lot of the discussion about voltages, so I don't want to spend more time on this. So you saw the discussion about phospholipid cathodes, but also for spinel cathode materials, it works very well. You see that DFT+U+V with self-consistent UNV gives very good agreement with experiments. You saw this slide also in the Professor Marzari's talk. This is formation energies of oxygen vacancies and perovskites. So this is the formation energy on the y-axis. and on the x-axis is the size of the supercell. The experimental dilute limit is this black horizontal line. Green star is the hybrid functional HSE06. And we see when we increase the supercell, both DFT and DFT+U, they go in the wrong direction. They go further away from the dilute limit, while DFT+U+V changes little, and moreover, it gets closer and closer to dilute limit and gives the most accurate results, as accurate as hybrid functional for small sizes of the supercell. There is a lot of discussion about band gaps. People like band gaps. So DFT+U improves band gaps. Doesn't give you perfect, very accurate one, but it improves with respect to DFT. And if you look at this table, we studied a bunch of systems. If you compare DFT band gap and DFT+U with orthoatomic orbitals, UTM, it means we applied Hubbard U only to transition metal, and U all, it means we applied U to transition metal and also light elements like oxygen, sulfur, etc. So we see that with orthoatomic orbitals, we get pretty close agreement to experiments, while if we use atomic orbitals, we are much more off. So this showed that orthoatomic orbitals are more accurate than atomic. Band gaps are improved, but they are still not perfect. And as I wrote on Slack, you should use better Koopman's functionals from band gaps, because Hubbard functional was not really designed to give you excellent band gaps. It improves, but it's not really the theory for band gaps. And it's another example about band gaps. I think I'll skip it. Also showing that +U improves band gaps. You go from 1.81 in DFT to 3.11 in DFT+U, while experiment is 3.3. So it's quite significant improvement, but still not yet perfect. And final example about magnetic materials, I would like to show you that DFT+U+V with orthoatomic orbitals is the most accurate approach. So this material, the beta phase of manganese dioxide, is known to be having very complex magnetic ordering. It's a non-collinear helical. You can see it's shown on the left, extremely complex one. But in practice, people use a simpler approach. They use collinear magnetic ordering and different types of magnetic ordering. So we consider 4 types of magnetic ordering called A1, A2, C, and G. All of them are antiferromagnetic, AFM. And we would like to check which of these 4 is the most energetically favorable. So the so-called good enough Kanamori rules, they suggest that A1 AFM should be the most likely configuration. And this is the one which is used in literature the most, A1 AFM, but we would like to check if it's really correct and which level of theory confirms that this is the most likely ordering. So on the figure on the left, it's a very busy slide, but it shows the difference between ferromagnetic and antiferromagnetic total energies for 4 types of magnetic ordering. That's why we have 4 colors. And we have 5 sections: the DFT section, DFT+U using non-orthogonalized atomic orbitals, DFT+U+V non-orthogonalized orbitals, and again +U+U+V with orthogonalized orbitals. So the positive values mean that AFM is more stable than ferromagnetic. Instead, negative values means that ferromagnetic is more stable than antiferromagnetic. But if you carefully inspect this figure, you will see that in DFT+U+V with orthogonalized atomic orbitals, we find that this pinkish bar is the highest, which means that A1 AFM is the most likely, the most stable magnetic ordering, which agrees with good enough Kanamori rules. But if you take other levels of theory like DFT+U, orthogonalized atomic, it wrongly predicts the green to be more stable, which is GFM. DFT+U+V with non-orthogonalized atomic orbitals completely fails because in many cases it's ferromagnetic, which is more stable. And in other cases, again, we can see that DFT+U non-orthogonalized atomic orbitals is pretty good, while DFT also pretty good, degenerate with A2F. So the bottom line, DFT+U+V orthoatomic is the most accurate. And if we look at the band gaps here, we see again that experiments are black horizontal lines, 0.26, 0.28, and we see that DFT+U+V orthoatomic is very close, 0.32, very close to the experimental value. We also checked alpha MnO2, but this is can be seen in the second reference here. Okay, and take-home messages. So DFT+U+U+V are accurate and computationally efficient to treat cell consistency error. Hubbard parameters are not universal. I hope you really take this with you after this lecture. Hubbard parameters can be computed from first principles. There are many methods, but here we discuss the linear response theory. We have introduced a new reformulation of linear response theory without supercells, and it is based on density functional perturbation theory with primitive cells and monochromatic perturbations, and it's implemented in quantum suppressor we will use in the hands-on. And finally, Hubbard parameters and Hubbard projectors must always be consistent. And I think now we can have some time for the discussions.
Thank you, Iurii. Thank you very much for this very clear talk. So yeah, there was a lot of questions in the Slack channel. Most of them has been already addressed, but let me just pick some of those that were not really answered yet. So one is from Jemo Lim. And the question is, will applying U and V to all atomic orbitals and allowing all anisotropy so that you have 4-indexed U, I, J, K, L systematically improve the result, or should one use some intuition to choose only a small number of relevant orbitals and parameters?
Okay. So first we have to understand how do we compute that U, I, J, K, L. So maybe using CRPA, but in our implementation, we can't resolve the Hubbard U so much. We have just the global parameter U that is applied for all states. But if we really want to fine-tune and resolve the value of U for each individual component that is not implemented, maybe this can be done. I don't know how relevant it is. So far we use, let's say, average approach, more simplified one where we use the global U. So I don't know how much we gain by doing that actually.
Okay, thanks. So let's go to the next one. So there is a recurring question that maybe it's good to ask it again, and if Matteo is still there, we can discuss about it. So the question is more related to the previous talk, but I didn't catch well how to justify physically to use an on-site U for covalent band insulator like silicon and gallium arsenide. So I guess this is a question for both you and Matteo. So if you want to comment, or if you have any comment.
Yeah. If you want to answer, Matteo.
So the question was, I didn't understand well.
How to justify physically the use of on-site U for covalent band insulator like silicon and gallium arsenide?
No, in fact, we needed the V there. And I mean, in the original reference, actually, I was planning to mention this afternoon, but we can say it now. Computing, actually what one needs is really to treat S state and P state on the same footing, because as we know, I mean, the balance states of this material is based on sp3 hybridization sort of thing. So in order to have a good representation of orbitals where the electrons like to localize, you have to mix them. And that means that in order to get an accurate calculation, you have to have both U and V, both on-site and inter-site. Basically, there's also a V on-site in some sense between S and P states that generalizes the usual approach. And it turned out actually back in 2010 that these values of U and V are very similar to each other. Okay, so if you the person goes to the reference of our 2010 paper where the plus V was introduced, you will find a section on discussing these band semiconductor.
Great, thanks. Then there is a question. Another method for computing U is the ACBN0 method and its recent extension to V. It is computationally very cheap as it doesn't require any response calculation. Could you compare it with constrained DFT?
Yeah, well, what I can say about this, we know very well this method. I mean, we're aware of this. Well, in our case, with linear response theory, the definition of U is based on the second derivative. So which makes a lot of sense, and we physically understand what it does. It's really removing the curvature, and this is how it's defined, and that's how we compute it. Instead, in ACBN0, the definition is different. Actually, to be honest, I never understood how is it defined, and I don't know if it really removes the curvature. I don't know. I know that it works well, and values of Hubbard parameters, I think, pretty close to what we obtain with linear response. But I need to understand better what is the meaning, how they define the Hubbard U parameter in ACBN0.
Let me comment a little bit more on this. So if you work out the explicit expression of our linear response calculation of U, you get a U that is again the later integral of the Coulomb interaction over atomic states, basically in the basis set that we typically use in DFT+U calculation with some screening. The screening that comes from considering all these states of one atom all together and average over them, etc. So that's pretty similar to what ACBN0 is based on in their calculation. What I don't understand of ACBN0 is the way of screening the effective, I mean the Coulomb integrals in order to get the effective U and V now. So they use atomic occupation somehow, but I don't remember the details, and I remember that the method is not too clear to me. So the details are not too clear.
No, same for me. I need to understand better.
So that it's the screening part that makes a difference.
So can we say that, I mean, in the linear response or constrained DFT, there is some very physical constraint that we want to enforce, that is this linearity of the energy, while there is not clear exactly what or the condition they force to get this U parameter. Is it correct or not?
Yes, I mean, one can argue that at the end they have similar definition of the parameters. Again, numerically they are different, and so the way screening is performed is different, and that's what makes a difference at the end of the day.
Okay. Okay. Then I guess most of the question has been already addressed, but you can check yourself actually. So I think we are perfectly on time, so we can close here this first part of this first session. Now we have a coffee break, so we meet again in 15 minutes.